All right, let's talk about something that sounds super simple on the surface, but is actually a really fascinating engineering challenge, figuring out how big a pipe needs to be to move gas.
I mean, it's one of the most basic questions a process engineer gets asked, right? Whether you're designing a massive pipeline or just a small line inside a plant, you have to answer this. And getting it right is, well, it's everything.
So here's where things get interesting. If you're moving a liquid, say water, it's pretty straightforward. Its density doesn't really change. We call that incompressible flow. But gas? Gas is a whole different beast. As it flows down a pipe, the pressure drops, the gas expands, and its density changes the entire time. That one little fact makes the whole problem way, way more complex.
To get a handle on this, engineers are basically fighting against two main constraints. You can think of them as the two villains of our story: velocity, which is how fast the gas is moving, and pressure drop, or how much energy it loses along the way.
Okay, so first up is velocity. There's a sort of unwritten speed limit. A really common rule of thumb is to keep the gas moving at around 30 meters per second, which is roughly 100 feet per second. Now, this isn't some magic number. It comes from a ton of real-world experience.
And here's why that speed limit exists. You can look at industry standards like API 14E. Now, this one was written for offshore oil platforms, places where people are living and working in tight quarters, and it points out that when you go too fast, things get loud. And noise isn't just annoying, it can be a serious safety issue.
But it's not just about noise. That's the key takeaway here. If you let the gas fly through the pipe too quickly, it can literally start to wear away the inside of the pipe. That's erosion. Or it can cause the whole pipe to shake and vibrate, which, as you can imagine, is not a good thing. So that 30 meters per second, it's really the sweet spot to keep all these problems in check.
Now for our second villain, pressure drop. Look, it takes energy to move gas, and that energy loss shows up as a drop in pressure from one end of the pipe to the other. And for this, engineers have a really useful shortcut. It's called the 10% rule. Basically, if the pressure drop is less than 10% of what you started with, you can kind of cheat. You can pretend the gas is an incompressible liquid and use much simpler math. But if your pipe is super long or you're just pushing a ton of gas through it, you're going to blow past that 10% limit. And that's when the cheat code expires and things get a lot harder.
So, what do you do when the simple rules of thumb just don't cut it anymore? Well, that's when it's time to break out the big guns, the more advanced physics, and the powerful tools that can handle it.
At this point, you just can't ignore the changing density anymore. You have to face it head on, and that means you need a much more rigorous, much more accurate way to model exactly what's happening inside that pipe.
And this is the engineer's toolkit for doing just that. You've got fundamental equations like Darcy-Weisbach. Then you have different models for different situations. For a really long pipeline, you might assume the temperature stays constant. That's an isothermal model. For a short, high-speed flow, like in a relief line, you'd assume there's no time for heat to transfer, so you'd use an adiabatic model. And of course, today we have amazing simulation software that does all the heavy lifting, even accounting for weird effects like the Joule-Thomson effect, where a big pressure drop can make the gas get dangerously cold.
Okay, so you run all the numbers, you do all the fancy modeling. You'd think you'd end up with one perfect pipe size, right? Well, not quite. Because at the end of the day, the final decision isn't just about physics. It's an economic balancing act.
And here's the fundamental trade-off. On one hand, you have your capital expense, or CapEx. A bigger pipe costs more money to buy and install right now. But on the other hand, you have your operating expense, or OPEX. A smaller pipe has more friction, which means you have to spend more money on energy, day in and day out, to run the compressors that push the gas through it.
And this quote just hits the nail on the head. The best design, the truly optimal one, isn't just the one that works technically. It's the one that makes the most economic sense over the entire life of the project. It's all about finding that perfect balance between the upfront cost and the long-term running costs.
And that really leaves us with a final thought about what engineering is all about. It's this incredible mix of hard science and very practical economics. The goal isn't always to find a single, flawless answer, but to find the most intelligent, the most effective compromise for the real world.